We are now going to discuss addition of representation in group theory. Okay, so you can forget everything that you learned till now and remember only these certain things that I'm going to tell you right now. So there are group elements that act on the coordinates and give you new coordinate. There are operator corresponding to these coordinate transformation. These operators, they act on the functions. Okay, and if you take a basis, so and that if you take a basis, for example, remember we took a basis like psi of x and psi of minus x when we choose to work with E and I, then you can always find a matrix representation of these elements based on the basis. Okay, so the core idea is, if this is how we are going to do the whole thing, then you always need a basis. This was not the case when we did the operations during permutation and on the equilateral triangle, because there was no basis there, no function there. In the equilateral triangle case, you had a group of operators that directly acted on the equilateral triangle. So at that point, we cannot say what is our basis, what is our function. Okay, and this is one more idea, that you have a vector space which is a collection of elements, and we are going to deal with linear vector space in more detail in the next part of the lecture. So if you have a vector space, so the whole idea is, if you are given with a vector space, what is a vector space? A vector space is a set which contains lot of vectors, and in the vector space you have operators that act on the vector space. So you have vector space, which is a collection of elements, and you have certain operators that acts on the elements of vector space. Then you can represent these operators in matrix form by using the basis, of the vector space. So this is the whole idea. So this is another idea. When you have a vector space, you have a group of operators, and you want to create a matrix representation of those operators that act on vector space, then you play this game of basis and etc., etc. Okay, so now okay, so I think yeah, let's go forward with the addition of representation. Okay, so what's the core idea? Let me tell you this. So we are going to consider 2 to 3 cases. Case number 1. So what we will do in case number 1 is consider we again have E and I. We are going to work with this. So E, when it acts on X, we get the same value X, and I, when it acts on X, I get minus X. Okay, now we are going to do a very interesting thing. Now we are going to change, we are going to take a function psi, which is even function. Now this will change the scene. Why this is going to change a scene? Let's check out. So what happens when OE acts on psi? You get psi, or more precisely, let me write it the way we understood it. So OE, when it acted on psi of x, you got psi of x. But OI, when it acted on psi of x, I think we got psi of minus x. But since psi is an even function, psi of x will turn out to be, a psi of minus x will turn out to be psi of x. So we do not have we do not have two bases like before. So there is only one basis So we have only one basis, which is psi of x. So now the problem is, if you have such kind of relation, which we didn't had before, if you remember, if you have such kind of relation, then how are you going to do the representation of the operators? Well, since you have one basis, the only way is you can do 1D representation. And in 1D representation, you can represent your element like dA. I'm writing A because A for 1D representation. This is going to be 1, and dAi is also going to be 1. 1 because in both cases you started with the function and you ended up with the same function. That's why the 1. Okay, so this is case number 1, where your psi is a even function. Now let us see case number 2. And in this case, let us choose our psi to be odd function. So what is a property of an odd function? That if you get psi of minus x, then it will be minus psi of x. Here also, let's act this operator on psi of x. You are going to get psi of x, and when we act this one on psi of x, we are going to get psi of minus x, but this is equal to minus psi of x. So unfortunately, again, you have one basis here also. You get the same result, but there is a difference in sign. So the matrix representation, and I'm going to use B, and we are also going to get 1D representation here because we have only one basis, and dB of E can be written as 1 because we get the same function, but dB of I should write it most probably minus 1 because I get negative of the function. So this is one-dimensional representation of your operators. Okay, now what we will do, we are going to look at the third case. So in the third case,
excuse me, why is it one basis?
Because if you look at here, how can you write it in terms of, because you have only psi of x coming out as output. If you look at the first case, the only output is psi of x, and the only function that exists is psi of x, because psi of minus x, which was the other function that existed independently before, but now because psi is an even function, it doesn't exist independently. Psi of minus x doesn't exist in fact when psi is a even function, because psi of minus x is also psi of x. The same thing happened here. Psi of minus x don't exist because it is minus psi of x, so you get psi of x again. So the second one, which existed before independently, because of our new constraint being psi as even or odd, the second psi of minus x is not linearly independent. You understood the word linearly independent?
Yes.
Or we will come to all this. Okay, now the third one. The third one is interesting. What we will do is we will take two functions. We are going to take two functions. Okay, and how the two functions are going to look. Let us take an even function, psi1. So by even function, I mean if you have psi1 of minus x, you are going to get psi of x. And we are going to take an odd function, psi2, such that psi2 of minus x is minus psi2 of x. As you can see, now we have two bases because these two functions, psi1 and psi2, they are linearly independent. Okay. Now let us act our operator. So what happens when OE acts on psi 1 of x? I'm gonna get psi 1 of x. That means I don't get the other function. What happens when OE acts on psi 2 of x? I think I'm gonna get psi 2 of x, and since I don't get this, so this is 0 into psi 1 of x. So now since psi 1 and psi 2 are linearly independent bases, can you now tell me what will be the two-dimensional representation of E? The two-dimensional representation of E turns out to be 1, 0, 0, 1. Easy. Similarly, let us work with OI. So OI, when it acts on psi 1 of x, okay, we have to be careful here. So we are going to get psi 1 of minus x. Okay, so what is psi 1 of minus x? Psi 1 was even or odd? So psi 1 is even function. So I'm going to get here what? Psi 1 of x. So let me write it as, so OI acting on psi 1 of x gives me psi 1 of x. That means I don't get the other one. So I can write it as 0 psi 2 of x. Similarly, when OI acts on the odd function psi 2 of x, we'll get what? Psi 2 of minus x, and psi 2 of minus x is minus psi 2x. So I'm going to get here minus psi 2x, but I don't get this one. So let me write it as 0. So what is the 2D representation? Let me write 2 here of I. I get 1, 0, 0, minus 1. Okay. Now if you look at, something interesting happens here. Something very interesting happens here. The interesting thing is this part, which is D2 of E, that is a two-dimensional representation of E, turns out to contain D A of E here, 0, 0, D B of E. So dA of E was related to what function? Let us check. dA of E dB. So dA of E was related to when psi was an even function. So that's why dA is on the top and dB is a representation related when psi was an odd function. Okay, so as you can see, the 2D representation of E can be written in terms of the 1D representation. Similarly, let's look at the 2D representation of I. If you look at this cleverly, then you will see that the first one is dA of I, and the second one is dB of I, because dB of I, we checked that it turns out to be minus with a negative sign, because we have a minus 1 here. Let me show it to you. If you look at this, see here. Okay, so now I'm gonna tell you some definitions, and I want you to keep that in mind, and so that we will understand it in a more clearer way as we move forward. So D1 of E and dA of E and dB of E, they are irreducible representation of E, and D2 of E is a reducible representation of E. So this is the core idea that I want you to keep in mind for now, and we will understand this in more detail as we go forward. So why D2 of E is a reducible representation? Because it can be reduced to two one-dimensional representations depending on, so you can have a basis where the operator, the action of E, can be represented in a 1D way,
Hello.
and it turns out that your 2 cross and it turns out that your 2 cross 2 matrix can be written in terms of the old representation when you had one basis. Okay, just keep it in mind. Only these words, I want you to keep these words in mind.
Can you repeat
I'm saying
your last sentences?
I'm saying that what is E? E is something that acts, it has a particular way of acting. It is a particular way of acting on objects. And depending upon what object you choose, you form a representation of E depending upon the basis. Now, what the interesting thing that we saw here, that if you use the action of E on a basis set which has two linearly independent functions which acted as basis, you got a 2 cross 2 representation of E. Okay. You can also have 3 cross 3 representation of E depending on your basis. So if you choose 3 functions as basis and all the 3 functions are linearly independent of each other, then you can have a 3 cross 3 matrix that tells you how your E is. So representation depends on the basis. Here we used 2 cross 2 representation, but we saw a very interesting thing, that the 2 cross 2 representation was able to be broken down. We broke it down into two 1 cross 1 representations. The first representation appeared here at the top and the second one appeared here. That means we were able to find, or we were able to reduce the 2 cross 2 representation to two 1 cross 1 representations. So such a representation, if you're representing your operator with a certain matrix, and if the matrix is reducible, then the representation that you started with is called a reducible representation. But if you look at dA of E and its one-dimensional representation, can you reduce it any further? You cannot. And that's why the 1D representation of E is irreducible representation. You cannot reduce it any further. But when you had 2 cross 2 representation, you were able to reduce it to 1 cross 1 representation. Maybe when you have
is it always possible for a 2 cross 2 representation to reduce it to 1D representation?
It is not always possible, but you have to see whether it is possible or not. If it is possible, then we say that it's a reducible representation. If not possible, then it's irreducible representation. For example, maybe you will have some group whose representation in 2 cross 2 is irreducible. So the group elements cannot be represented as 1 cross 1 matrices. Maybe you can have that. Maybe you can have some group elements whose irreducible representation occurs in 3 cross 3. You are not getting any representation of the element in 2 cross 2 or 1 cross 1. Okay. So that's how we understand. As I'll give you more example, we'll understand better. Okay, let's go forward. Now if you choose 3 functions, say you choose psi1, psi2 and psi3. So now you have 3 functions. So it's a clear indications that we can have 3 cross 3 representation. What you do is take psi1 and psi3 to be odd functions, and take psi2 to be even function. Okay. Now can you tell me what d of I can probably look like? So when d of I acts on psi1 is an odd function, so you'll get a -1. Okay. The second one is psi2, which is an even function, so you will get the same function here, and then you'll get again -1 with the third function. So if you compare it with the old representations, then I think this is d bi 0 0, this is d1 da I 0, and then this will be again db I. So you see, even if I choose 3 bases, but the 3 bases were chosen cleverly, being odd or even. Why I choose odd or even? Because I already knew how they act on odd or even functions before, and I cleverly chose this basis, and I knew that since there are 3 linearly independent bases, I'm surely gonna get 3 cross 3 matrix. But since my basis was cleverly chosen, and I was able to see that the 3 cross 3 basis, 3 cross 3 matrix representation was a reducible representation. Okay. Now what happens when you start with say 4 functions? So if you start with 4 functions, you are going to get 4 cross 4 matrix representation of the operator. So as you can see this, the operator is the same, its way of behavior is the same, but the representation is different. How can I give the example? For example, I'm not getting any example to say, but I hope you get this point. Okay, so let us choose 4 functions, and let us choose the 4 functions in such a way that neither of them is an odd function or even function. Okay, so consider I choose psi of x, and since psi of x is neither even nor odd, so psi of -x has an independent existence. Let me choose phi of x, and since phi of x is neither odd neither even, so phi of -x has an independent existence. Okay, now if you have 4 functions like this, then you can easily form 4 cross 4 representation, and how it's going to look? It's going to look like this. You can easily check. Okay, so how you can check? Just make your OE act on psi of x, and you know that you will get psi of x, and others are 0, so just write others here, psi of -x, then 0 into phi of x plus 0 into phi of -x. In this way, carry forward, you just continue doing it with other functions, and you will get your 4 cross 4 representation. Okay, now here there is a very interesting thing, that I can put some dotted line here, and I can put some dotted line here. Oh, why dotted line? Let me put straight lines here and here. Oops. Okay, let me do a different color. So like this and like this. So what do you see here?
D2.
I think we are looking at the existence of D2. Yes?
Yes.
Let's look at the four-dimensional representation of I. So d prime I, it's gonna look at 0 1 0 0 1 0 0 0 0 0 0 1 0 0 1 0, and again let's divide them in this way. Do we see anything? I think we don't see anything that had 0 1 1 0 to do something with I. But anyways, so what do we understand? We understand that the following. If you go to the previous page, so from here we understand that you can add representations and make a new representation. Again, we understand that you can add representation and make new representation. For example, if you look at dA of E and dB of E, using these two representation, I have a new representation d2 of E. This is in short written as like this. So d2 of E can be formed by adding dA of E representation and dB of E. We'll come to all this again in future course of time. Okay, this is called addition of representation. So if you have old representations, then you can add them and get new representation. And what is the interesting thing? The interesting thing is that you can have a 2 cross 2 representation of d2 of E, and it and the behavior of d2 of E and d1 of E will remain preserved. For example, these are elements, right? Group elements. So if you have I and E here, whatever the behavior of I and E is there, for example, closure, associative, the representations also take on the same behavior, and we are going to prove it. So now my task is to prove that if I make matrix representation of group elements, then they also satisfy the same relation as the group elements. This is a task. Before that I did it with the operators, and now I have to do the same calculation, but this time with the matrices. Okay, fine.
Excuse
Any doubts
me.
with you?
Isn't there any limit for the dimension of representation? For example, you wrote 4D, we can write 5D, 6D, 7D.
Yeah, so depending upon what kind of vector space you choose and what are your bases, you can make any dimensional representation. So the idea that you are representing an operator is based on the fact that you are using which vector space to represent it.
But we have the lower limits, but we don't have the upper limits.
Yes, we have lower limit, but it may not be the lower limit for every group. Maybe there are some groups that have that become irreducible representation when you are at 2 cross 2.
Yes.
Okay, maybe I'll try to find some examples for your question.
Okay.
Okay. Okay, now I need to prove that the elements, the matrix element, they form the same operation like the group elements, which is very crucial to check. How do I do it? So I do it in the following way. Let me use green. Okay, so can I write this form? OR psi of nu is equals to summation mu goes from 1 to n psi mu d mu nu r. Now what does this mean? Okay, I have to start with this, but I have to tell you what does it mean. It means the following. So if you remember, when we had the basis psi of x and psi of minus x, the first example that we took, then we saw that d of e under such basis was represented by matrix 1 0 0 1. Okay, how we were able to derive this? We saw the action of operator on the function, and it turns out to be this. But I can write this using the matrix here. So how can I write this? I can say that OE of psi of x. So imagine that this is function f1 and this is function f2. So let me write it in this way. So OE on f1 can be written as fj dji summation j goes from 1 to 2. This means the same thing as I've written above. So this is the same thing as this. Is this clear?
Yes.
So why there is an n here at the top? If I have a vector space with n basis elements, then my representation is of course going to be n cross n. So this is just a generalization to a vector space with n dimension. So dimensions of a vector space means how many bases you have. Okay, so this idea, this is clear, right? What I have written here is clear. Now this is a representation of one operator. Now to show that the operators satisfy the same behavior as the group elements, I need two of them. Okay, I need two of them and I need to work with two of them. So let me work with both of them. So I'm going to choose two operators, OS, OR, and their corresponding matrix representation in n cross n as d of s and d of r. It would be better if I write n here, but I'm going to drop this because it will unnecessarily make it look clumsy. So now what I want you to do is start with this. Let your OR act on a basis state psi mu, and this can be written as a combination of various bases psi mu. So mu goes from 1 to n with some coefficients. So the elements of the matrices are just coefficients in front of the basis. Okay, and mu nu both go from 1 to n. So if now consider I have OSR acting on nu. What I want to say is, consider I have some operator C which acts on psi nu, and I know that C is equal to SR and C also belongs to the same group. Okay, then let us look at some of the mathematics here. I know that I already have shown that the operators they are good because I have shown that they can be written in this way just like the group elements. I have already shown this before, that the operators satisfy the same relation as the group elements. Okay, so if SR belongs to the group, then I can write S and R and multiply them separately, and they all belong to the same group. Okay, I have already shown this. me remove it. So now, since I already know this, I can do one more thing. I keep the OS here and I look at the action of OR on psi nu. I know that the action is summation mu goes from 1 to n psi mu d mu nu of r. I know this. Now what I'll do is I'll make OS act on psi mu. So keep this here, mu goes from 1 to n, and I'm gonna make OS act on psi mu, and I'm gonna keep this matrix outside here. And this is quite easy. So 1 to n, I can introduce sigma goes from 1 to n, and this thing will become psi sigma, and there will be a matrix D sigma mu S and D mu nu of R. Okay, so what I can do here is I can see if I compare it. So if the mu is repeating here, that means this is related to the summation. So I can write it in a much better way. Keep the sigma summation outside, psi of sigma, and take the sigma summation with respect to mu inside when you are dealing with the matrix. And I could have followed Einstein summation convention, and frankly I should not have used summation again and again, but just for convenience. Now what you do is, now you look at, now you compare it. Okay, compare it with what? Now assume that this is a matrix and this is actually matrix multiplication. If you do matrix multiplication and write it in tensor form, this is how it looks. Okay, so since this is also a matrix, you can give a name to it. Let this be D sigma nu of SR. Okay, now you make comparison. Now it's very easy. If you look at the final, if you look at what we started with and what we ended with. So we started with OSR acting on psi of nu, and then we reached till a point where we had such kind of relation. I'm dropping the summation for d mu nu S and d mu mu R. So sigma mu and mu, and there is a summation with respect to mu. And I said that this is nothing but your matrix multiplication, and name it d sigma nu. Now what do you see? You see that the new matrix that represents SR, or more precisely the new matrix, which is a matrix representation of C, because SR is equals to C, that belongs to the group. So when you multiply two group element and you get a new group element, the matrix representation of that element turns out to be the matrix representation of the S multiplied with matrix representation of R. That's it. You see, even the matrix representation, they follow the same group operation like the group elements. So we saw that the operators, they satisfied the group relation. Even the matrices, they are satisfying the group relation. That means if you know two elements G1 and G2 belongs to G, and you know the matrix representation of G1 and you know the matrix representation of G2, if you multiply them, then you will get the matrix representation of G3. Now what is G3? G3 is another element of G which can be found out when you multiply G1, G2. more precisely. Remember the group we discussed, R, W, E, sigma prime, sigma double prime, sigma. So if you know the representation of R and if you know the representation of W, then you know where RW goes. You say RW goes to some element, then the representation of that element can be calculated from here. So you don't have to do the whole calculation for all the group elements that we did before. If you already did some group representation of some elements and you know certain relations, you can find the matrix representation of other elements using this property. Any doubt till here?